Next, I'd like to introduce our sponsor, from Ford Motor Company, Craig Stevens. Craig joined Ford Motor Company in 1987, working in the powertrain, calibration, and controls group for Ford in Europe. And in 1991, he moved to Dearborn and led the worldwide company effort to develop common powertrain controls, algorithms, and software. From 2001 to 2009, he was the manager of powertrain controls in Ford's research and advanced engineering facility. He held the position of assistant chief engineer for global powertrain until 2012 and is now the chief engineer for controls, engineering, research, and advanced engineering. We welcome Craig Stevens from Ford Motor Company.
Good morning. It's a pleasure to be here representing Ford and talking to you about some of the things that we're passionate about. So I think it's very appropriate that we're here talking about robots transforming lives, because at the end of the day, it is about people. It is about some of the people who are here in this room. And if we can start the presentation, we'll talk about the need for engineers. It was mentioned that one of the things that's slowing us down is the lack of engineers, and this is a serious problem that we need to address. These statistics on the right-hand side, you see that so few people are going into it, science, technology, engineering, and math, and it's been declining over the years. And if you look on the right-hand side of this graph, you will see that the demand for engineers is growing, and that is one of the things that is really critical that we address. And Debbie mentioned this in her speech. If you look at where the US ranks, we're not where we need to be. This room, unfortunately, is the group of people that's already converted. You understand the importance of science, technology, engineering, and math, and you're part of the future, but we need you to talk to other people and get other people interested. So one of the things that's really important to us as being an automotive manufacturer is to get people to come into automotive. We are at a level of unprecedented challenge in our industry, but people have an outdated view of what the auto industry is. For a lot of people, this is what people still see. They think of brown, grey factories. They think of dirty, noisy, greasy, dangerous assembly lines. That's not what the auto industry is about today. This is what the auto industry is about today, and this isn't a new trend, but it's a trend that's accelerating. The electronics, the software, not just in the car, but in our factories. Look at the picture on the bottom right there, and you see the sparkling, shiny floors. I'll come back to that in a little while. But what's driving all of this technology in automotive? Well, it's society, right? It's people, it's governments, it's regulators, it's cities. Fuel economy is something that we've been concerned about for decades now. And fuel economy is going to carry on being a concern. Even when fuel cells are here, energy is still going to be something that we need to manage in the context of mobility. We talk about connectivity. We know that we live in a connected world. Nobody can go anywhere without their cell phone these days. My kids, the only thing they care about when we go somewhere is, where's the Wi-Fi? We're connected in everything that we do. Cars are becoming connected. Today, in small ways, they are giving vehicle health reports. They're able to allow us to play music for our MP3 players. They connect wirelessly to Bluetooth on our cell phones. But in the coming years, cars are going to talk to each other, cars are going to talk to infrastructure, and they're going to start to cooperate, and they're going to start to solve some of the big problems that we have. We're fortunate. We're here in Ann Arbor. Ann Arbor doesn't have great traffic problems. But if you go to some of the mega cities of the world, then cars are a huge problem. Congestion, the time people spend in their vehicles trying to get from A to B. And so mobility is becoming a growing concern. That's interesting to us at Ford because if you go back to 1925, there was an advertising poster for Ford that talked about opening up the highways to all mankind. You know, we weren't trying to create vehicles for the elite. We were trying to create vehicles for the masses. That's what Henry Ford was all about. That's still part of our mission today. And when you look at some of the big mega cities, you look at Sao Paulo, you look at Shanghai, Beijing, you look at London, you find that cars are actually becoming an impediment to people's mobility. And so for us as a company, mobility is a really big, important part of where we're going in the future. And technology, connectivity are going to be the things that help enable that. I'm going to come back to autonomy, so I'm not going to talk about that now. So let's go back to the students that are here in the room, and let's talk about why Ford is interested in FIRST. Well, one of the primary reasons is it's cool, right? FIRST robotics events, as Debbie said, are just fantastic places to go to see the same energy at an engineering sport that you would see at a basketball game or a football game. Is just fantastic. But there's more to it than that. This is the mission of FIRST, and it encapsulates so much of what is important to us and what is important in industry. It's about the engineering challenge for sure, but it's about other things as well. It's about the fact that there is never enough time. There are never enough things in the warehouse for you to go and build your robot. You can only get there if you have a plan, you have a strategy, you have great teamwork. And at the end of the day, when it comes to your event, your robot isn't going to work unless it works as a system. It's not going to work unless it's safe, unless it's reliable, and unless you had teamwork to get there. So it is a microcosm of the real engineering world. And that's one of the reasons that FIRST, and it's not the only robotics program, they all have some of these same goals, and it's fantastic. And it provides results. And just here are some of the results. This underscores why things like FIRST are so important to us. And it cuts across the board. And I'm preaching to the converted here. I see lots of people who are engaged in FIRST already, but we need to still get more people interested. So I'm going to switch a little bit and talk about Ford and the University of Michigan. We have a very long history together. We have had an alliance together, a formal alliance since 2006. We have active projects that we use to develop real new technologies that we then fast track to production, but it also gives us insight into some of the things that are going on into the university. It allows us to form relationships with the students, and that is part of our pipeline of new talent. And it's not just the University of Michigan, but it's others as well. I'm going to talk a little bit about something that University of Michigan has done that we're really excited to support. And this is about Southeast Michigan, the Michigan Engineering Zone, set up by U of M, right in the heart of Detroit, to really start to bring some of the high schools in Detroit back into what is the core of what Michigan is. And it was established in 2010, a partnership between College of Engineering here and Detroit high schools. There are 17 Detroit FIRST robotics teams there. Ford sponsors them all. It hosts a summer science camp, and all the students are eligible to receive Ford STEM scholarships. FIRST is really important to us. We have 50 teams that we sponsor in Michigan now, and that's just in the FRC competition. There's nearly another 50 in FIRST Lego League, FIRST Tech Challenge, and so on. And we would be really excited to try and grow that, and to try and grow that into some of the other robotics activities. I think if you're going to the state championships this weekend, I think there are 11 Ford teams that will be there, and we hope that they do well. Okay, so if you're thinking about this and you're a student here, you're probably already thinking about perhaps a career in engineering, science, and technology. But did you ever wonder what your robots would do if they could grow up and go out into industry? So what I'd like to do is show you a short video that shows robots and semi-autonomous assisting robots all working together with people.
This plant has a tremendous legacy. Prior to this aluminum truck, we built a steel truck for 10 years.
Today's truck delivers all the refinement that you could find in a luxury car, yet capability that you couldn't have imagined 10 years ago.
Well, this was a really big decision for us to go to an aluminum pickup truck. We actually started the planning and manufacturing for it about 4.5 to 5 years ago. And at that point, what we really focused on was our ability to have the technology to build aluminum or make aluminum at this level of capacity. Aluminum had been done in the industry before, but at really low volume. So obviously in the role of manufacturing engineering or in the role of plant operations, you need to be concerned about your ability to deliver it. The overriding spirit of camaraderie and teamwork and a plan to succeed and win really rallied us to know that we would do it, and we would do it as a team. If you were in this plant a couple months ago, you would see steel trucks going down the line, you'd see sparks, and the joining technology we would use are spot welds. And we don't do that, as you can see. We use screwing now, and we use rivets, and we use adhesive. The elimination of the welding has improved the working environment. Plant's cleaner, there's no welding slag, there's no sparks. We've spent a lot of time thinking through what's the right balance between a robot and a human. We use the robots to do the difficult jobs, the ergonomically difficult. We don't see a world where auto plants will be all machines without people. We actually grew the workforce by 850 people, but at the same time we grew our level of automation.
This is a once-in-a-career type of change. You don't introduce a new F-150 with new materials and new manufacturing processes, and to be doing it on the highest volume vehicle in the market is just an incredible experience.
We believe we've taken the truck to the next level.
We have a saying at Ford that leaders lead.
I believe you'll see the industry follow. You'll see the technology follow. You'll see the lightweighting follow. Success breeds that. And we've got a very successful vehicle here.
So I didn't collude with Rick or Debbie, but I think that picks up on so many of the things they talked about. That talks about how robots can work with people to do great things. That truck couldn't happen without those people and without those robots working together. And it wasn't just the putting the vehicle together, it was delivering the stock to the line, it was providing mechanical assistance to people lifting and moving heavy parts that they wouldn't be able to lift by themselves. And it's about manufacturing. But I actually work on the other end of the stream in research, and I work on control systems. That's been my career. So what I'd like to do now is give you some insight into how control systems have developed and how that takes us to autonomous vehicles. So this is where I started. If you listened to my bio at the beginning, most of what I've done is powertrain controls. When I joined Ford, the big challenge was to reduce the emissions of vehicles, and we have made enormous progress on that over the years, and we continue to do so. And that was about controlling very precisely the fuel going into the engine, how it was burned, and then how we processed those exhaust emissions to turn them into something that was less harmful, less damaging to the world. Things moved on very quickly, and we moved into networks with computers talking to each other on the vehicle. Perhaps one of the first examples of a feature would be anti-lock brake systems, where you have the chassis controller detecting that the wheels are starting to slip, and then sending a message to the powertrain controller saying, hey, can you reduce the torque right now because we need to bring stability back to the vehicle. That has grown enormously to an enormous system of networked computers all talking to each other on the vehicle. That takes us to being able to have the vehicle start to help the driver take care of itself on the road. Looking here, you can see the vehicles are starting to sense other vehicles on the road, providing the driver more information. I'll come back to these driver assistance technologies in one of the coming slides. That leads us to, one day, fully autonomous vehicles. This is our hybrid autonomous research vehicle, and I'll have some more pictures of that shortly. And that is going to help us to solve some of these mobility solutions. When autonomous vehicles can communicate with the cloud, get instructions from the cloud, communicate with each other, we can now start to tackle some of these bigger problems. But we can only do it if we have people with the right skills. So I stole this from Wikipedia, but it shows so much of what we need to make these things happen. It's not about just robotics engineers, but it's all these engineering disciplines coming together. I happened to start as an electrical engineer, but then moved into control systems, and along the way I had to pick up some of the other things in mechanical engineering, computer science, and mechanical CAD and so on. These things come together, engineers with diverse backgrounds, diverse skills, all working together. And it is that diversity that is going to provide the spark of innovation to solve some very, very tough problems. So let's go back to driver assistance technologies, because these are the things that are going to take us towards full autonomy. Let's define them first. Why would we want driver assistance technologies? Well, two reasons. The first is to help drivers avoid accidents. I already spoke about anti-lock brake systems. Many of us who are seasoned, I think is the right word, will remember that when we learned to drive, we were taught something called cadence braking, where you have to pulse the brakes if you end up in a skidding condition on ice. Most people don't need to know that anymore because your anti-lock brake system does it for you. But the other thing is we need to reduce some of the stress of driving. If you're driving in a city, if you're driving on a freeway, this can be some very stressful things for a lot of people. And electronics and software and computer science can help do that. So let's explore some of these technologies that are out there today. Adaptive cruise control. Vehicles have had cruise control for years. Long before we had electronic control of engines, we had cruise control. Well, one of the problems with cruise control is that it's limited in where you can use it. If you're in traffic, if the road is busy, it's hard to use it. But what we can do is we can add a radar unit in the front of the vehicle, behind the bumper, behind the grille, that can actually see vehicles ahead, and therefore can not only try to maintain the right speed that you want, but if there's a vehicle in the way, it will slow down and maintain a set distance. If we have a radar unit on the front, even when cruise control isn't engaged, couldn't that radar unit look out for the vehicle in front? And if you're approaching the vehicle too fast, couldn't it alert the driver that a collision is imminent? In our vehicles, we do that with a loud warning chime, and also we flash a bar of very bright LEDs on the windshield in front. That gets us to both some driver assistance and some active safety features, but it's still thinking about the vehicle just moving longitudinally along the road. We could add lane keeping, right? What if we put a camera on the front of the vehicle that could detect and see the white lines, and could actually, through the use of electric power assisted steering, give the driver some feedback if they're starting to wander off the road? Or perhaps give them a little nudge to steer back into the lane. Put these things together and you can start to see that maybe in the not too distant future that there are features out there that we could engage when we get on the freeway, and perhaps the vehicle could take us from the freeway on-ramp to the freeway off-ramp without us having to touch anything. Think about how that would reduce driver fatigue, boredom, the things that start to contribute to accidents. But that's one area of driving. There are other things that are quite stressful, and I think if I did a show of hands here about what's the most stressful thing of driving, I think many people would talk about parking, right? So we have active park assist. This is in production today, and going back to what part of our mission is we want this to be available to everybody. You can buy this feature on a Ford Focus, not just on a high-end Lincoln. And active park assist uses ultrasonic sensors. You can see them. They're mounted typically in the front and rear bumpers of vehicles. And if you drive along and ask the system to search for a space, it will measure the spaces between vehicles until it finds a space that's big enough to park in. When a space has been found, it will ask the driver to take their hands off the steering wheel, place the vehicle place the vehicle in reverse, and then the driver will control the speed, the braking, the shifting, whilst the vehicle does all the steering to give you perfect parallel parking every time. And we're building on that now. Very shortly, we'll have vehicles that once you're parked in, well, why not have the vehicle help take you out as well, right? Missing the car in front and the car behind. And then that other parking situation, perpendicular parking, that will be there soon as well. So those are a couple of things that are taking us into driver assistance and active safety. These things are going to continue to build on themselves, and we will find vehicles that have higher degrees of semi-autonomous capability. This vehicle, Ford Fusion, this is a 2013, so it's been out there a couple of years. This shows a lot of the things that we can do today. It has ultrasonic sensors to help with the parking. It has a camera to provide the lane keeping. It has the front radar. It also has two radars on the rear, and they do a couple of things. Those radars can tell you if there's a vehicle in your blind spot. Typically we do that with a little LED in the door mirror. And if you're backing out of a space, backing out of a perpendicular space, they can warn you of vehicles or people that may be approaching from the right or left where you don't have the ability to see. So I'm going to come back to a picture of a fusion very shortly, but let's look at why we might want cars that drive themselves. We've talked about some of this already today. The first is to reduce accidents. The statistics of accidents are really horrifying to us as a society, and we need to use what we can as engineers to help reduce that. That's been a long-standing trend in automobiles from when we introduced seat belts all the way through to some of the technologies I just talked about. A virtual driver can have more capability than a human driver. The ability to see 360 degrees around the vehicle all the time, right? That's something that no human can never do. Always be vigilant, not fatigued, never distracted, and those things can happen to everybody. That's not just about irresponsible use of cell phones or texting. It's about people who may be driving long distances and may be getting tired. It may be some looking at the vehicle over there, you're worried about it, but the accident's coming from the left. This is something where electronics and software can really help, and the right sensing methods. Every car can have an expert driver programmed into it. Imagine that, right? Not everybody can have the skills of a rally driver or an autocross driver. But when a car gets into a limit handling situation, the car hits ice, wouldn't it be great if we could have that expert driver on hand to do the best things possible that we could with the vehicle in that situation? Second reason, help the driver out. Driving can be stressful. Driving can be boring. One of the reasons I joined Ford is I love cars and I love to drive. But let's face it, driving long distances on freeway can really not be described as fun. Sitting in a traffic jam when you want to get from A to B, that cannot be described as fun. So these things are taking away the fun to drive that's so important to us in our vehicles. As engineers, we have ways to help people deal with that. But we can also use it to help solve some of these broader mobility problems. And these are going to take years and decades to solve. This is a journey, right? This isn't something where we're going to wake up one morning with autonomous vehicles and all the mobility problems will be solved. This is something that I don't know who the youngest person in the room is here, but there's an opportunity for you to help someone solve some of these mobility issues. Reduce congestion. We can do more efficient driving on the roads. We can have vehicles that drive very close to each other because they don't need that minimum separation distance, because if a car up front slams on its brakes, every single vehicle in the train will know that. We can have car sharing, right? For what about the situations where, I really don't want to drive my own car. I just want to get from A to B. I live in a city, maybe I don't even own a car, but sometimes I need one. What if I came out of my house, the car had shown up by itself, and it was going to take me from A to B, and then go find somebody else and take them where they want to go? More efficient parking. Not only is parking stressful for people, but parking is stressful for municipalities. Parking, look at the area around the University of Michigan here. How much of it is devoted to parking? How much time do people spend in the rain today walking across wet parking lots trying to get to and from their vehicle? It's not too far in the future that a vehicle will be able to drop you off at the entrance to the building, go and park itself, and then come back at the end of the day. And the other thing is that we will be able to use these features to help save fuel and reduce congestion. So, Ford has been involved in autonomous driving for some time. Some of you may remember the DARPA Grand Challenge. The first one was held in 2005 out in the desert. Ford reached the finals in that, and in 2007 in an urban environment. That was an F-250, and looking at the vehicle, you reckon we almost needed an F-250 just to be able to house all the kit that's on it. If you look at where we are today, we then moved on to a Ford Escape. That was something that we developed with U of M, and they're developing further technology with it. And at the end of 2013, we announced our autonomous fusion hybrid vehicle that we're doing directly in partnership with University of Michigan. I'll come back to that, why we might have chosen University of Michigan later on. So we have a long history in autonomous vehicles, and we're continuing to develop them. Here is a picture of our vehicles. So very similar to that 2013 Ford Fusion that I showed just a couple of slides ago. And underneath, it is a regular hybrid Ford Fusion. But as you can see, it's got some other things. And some of those other things are actually on the top. They're not antlers. Those are LiDAR units. And what a LiDAR is that it is like a radar, but it operates using a laser. And we have 4 of them. We don't plan on putting them there for production, and we may not have 4 of them. But for what we're doing right now in terms of research, this is very valuable. 2 of them are just pointing out to the sides, giving the view around the vehicle. 2 of them are on an angle. This gives us the ability to see down to the sides of the vehicle, gives you a better close-in view, but they also give you a view of the buildings and the rest of the surroundings. And I'll explain why that might be useful a little bit later. So let's talk about LiDAR. It was already mentioned that what we have in a LiDAR unit, that's what you might see. If we had one of these Ford Fusions in the middle of the room and we were here at night, we closed all the blinds, we turned off all the lights. This is what a LiDAR unit can see, and this is why we're so interested in LiDAR, because it can see in the dark. And what you can see there is a vehicle parked in a room. You can clearly see the people moving around. It was a display setting, so you can see some of the displays. The only reason it can't see more of the people there is because some of the people are forming shadows, right? So the LiDAR can't see behind. So in our vehicle, we have 32 lasers in each one of those units. They fire 2,200 pulses of light per second, and the sensor makes 10 revolutions per second. So if you can do the math, and I wrote it down, that gives us 2.8 million distance measurements every single second. Those are coming in. They are fused with information from radar, from cameras, from the GPS, from accelerometers on the vehicle, to really give us an accurate picture of where the vehicle is. So that picture up on the top right, that's a little bit artificial. And I've got one more artificial picture to show before I show you something a bit more realistic. It's a very important building to me. This is Ford World Headquarters in Dearborn. And once you start to drive around with these LiDAR units on top of the vehicles, and this was the purpose originally for LiDAR, it was to help with mapping. You can start to build these highly accurate, detailed maps of the world. Something much more detailed than what you see in your car navigation system. That's going to be critical. You can see there out front of World Headquarters, you can see the trees, you can even see the flagpoles that are out the front. But let's translate that into a more realistic situation. This is downtown Ann Arbor. I don't know if it was night or day, that's not important. But the way we use these LiDAR units is we're even able to pick up the reflectivity of the road. And so what that means is I can pick up the white lines. I can pick up the edge of the road. I can pick up the other vehicles in my lane and coming towards me. I can pick up the pedestrian crossings. These things are going to be absolutely fundamental if we're going to be allowing autonomous vehicles on the road. Okay, so that's LiDAR. What do we find on a vehicle if we want to make it autonomous? It's a lot more than what I showed in those semi-autonomous features. I've talked about the sensors. Sensors are fundamental. We also need high-definition maps. The vehicle has got to know exactly where it is, just as you would if you were a human if you were driving the vehicle. And that's the easiest thing to, when you think about an autonomous vehicle, is think about what you do as a driver, because an autonomous vehicle is going to have to do all of those things. If I have sensors and I have a high-definition map, I can do what is called localization. I can place my vehicle very precisely in the world that it's living in. And that's within centimeters, right? You can't do that with the navigation system that you have in the car that relies on GPS. But you can if you have this extra sensor set. That now allows me to plan a path for my vehicle. Think back to that picture of downtown Ann Arbor. If I wanted to turn left, I need to know that firstly the car in front of me is going straight on because he's in the going straight ahead lane. And I need to know that there is a turn left lane. And I've got to make a plan on how I'm going to get into that turn left lane. What if there's a pedestrian in that lane? What if there's construction in that lane, right? So I have to make a path that's going to allow me to get to my destination. There's more to it than that. I have to detect these obstacles, right? So that's why LiDAR, radar, camera, all of these things are important, right? Because these things are dynamic. When I go down the street today, it may not be the same tomorrow. There may be construction, there may be a broken down vehicle. Driving rules. These are things that are built into the way that we live our lives. Some of you here may be about to pass your driving test, so you're very in tune with the rules. Hopefully those of us who passed our driving test a little longer ago are seasoned drivers, as you might say. Hopefully we're still conscious of the rules. But there's more than just rules. What happens when 4 vehicles all show up at a 4-way stop at the same time? It does happen. How do we not end up with gridlock? Well, people signal to each other. Somebody will be brave. Somebody will brave and say, I'm going. Other times, people will wave each other on. How is an autonomous car going to understand what that wave signal means? Or conversely, what about when there is a policeman standing in the middle of the road on a green light with his hand up like this, right? So there are other things that require additional processing, and our intuition that we have as humans that allows us to be good drivers is going to be important as well. So we bring together driving rules, we bring together path planning, obstacle detection, and we now have an autonomous vehicle. Only then can we get into path following. And path following is about picking that route through the traffic, through the town to get to your destination. But it's a little bit more about that. It's about positioning the car on the road in the right position to be able to give the sensors the ability to see as much as they can. It's about working cooperatively with other road users. I mentioned this early on, but one of the other technologies that's going to come with autonomous vehicles is the ability for vehicles to communicate to each other, and the ability for vehicles to communicate with the infrastructure. What might that mean if a vehicle can communicate with each other? Well, I talked about one thing, right? If you have vehicles that are doing what we call platooning, driving very, very close together, if the vehicle at the front needs to brake, it needs to tell all the vehicles behind that it's braking. But then there are other things. If you're trying to overtake a truck, oftentimes you can't see the vehicle that may be coming the other direction. So you have to sort of nudge your way out. You've got to look and see if you can see the vehicle. If I have vehicle-to-vehicle communication, then I can actually have information to know whether it's safe for me to overtake. Other things, what about traffic lights? Well, traffic lights, you could say, well, aren't a big problem. Won't an autonomous vehicle recognize a traffic light and stop? For sure they will. But if I actually want to improve efficiency and fuel economy, wouldn't it be really handy if I could adjust the speed of my vehicle such that I know when that light is going to turn green, and I could time my arrival at the light so that I could go through it at green. I wouldn't need to waste all that energy coming to a stop and then restarting again. So vehicle-to-vehicle communication, vehicle-to-infrastructure communication is something else that's coming. That will be a different cast of characters, a different group of engineers working on those problems. And it won't just be the engineers, right? Because this is something that requires auto manufacturers, it requires governments, it requires all kinds of cooperation, it requires concerns around privacy to be addressed, data security to be addressed. All of those things need to happen, and we need to see a proliferation of the technology out, not just on the new vehicles we produce, but hopefully on some of the vehicles that are already there. There's an exciting pilot that's been running in Ann Arbor. I think it's got around 5,000 vehicles that have a pilot for vehicle-to-infrastructure and vehicle-to-vehicle communication. So these things are starting to happen. Okay, so I know where my vehicle is going to go. Now I've got to control it. Well, that means that I need to have a steering system that I can control electronically. We have those now. I need to be able to control the brakes electronically. We have those to some extent now. I need to be able to control the throttle, and I need to be able to control the shifting. Those are technologies that are relatively well understood. They're not yet at the level where we're ready to put them on an autonomous vehicle, but they're very close. Good engineering work will get them there. Our car, if it's got a virtual driver, is going to have to do other things. We'll have to turn on the wipers when it's raining, just so the people can see out and so the camera can see out. It will have to use turn signals. It will have to do all kinds of things that we take for granted today because we do them. Okay, so how are we doing this with the University of Michigan? We have had this long partnership. I talked about the DARPA Grand Challenge. I talked about our 60-year history with the University of Michigan. I talked about the escape, but why the University of Michigan? It's not just because it's just down the road from us. That helps. But it has world-class robotics expertise. And it has two professors that we've collaborated with. Long-term, we collaborated on DARPA, and they are a key part of our engineering team. This isn't a Ford team and a University of Michigan team. We're really working together. We have a U of M project. It's called the Next Generation Vehicle Platform for Active Safety and Driver Assistance Research. That's a mouthful, but it does describe everything that we're trying to do. We have other university partners who are helping us with other aspects of the challenge, but one of the key things that U of M is helping us to understand how can we get a vehicle to understand its surroundings, how we can get the vehicle to localize itself into the environment that it's in. And I think there's a talk later on today about the University of Michigan Mobility Transformation Center, a center that's being built just a few hundred meters east of us here, something that we're excited to support. And this test facility is going to help us to not only develop the technology, but to subject the vehicles to all the kinds of events that happen in the real world but don't happen very often, right? If we're going to do our testing, we're going to need to run many of these tests before we're going to let the vehicles go out on the public road. That's what this center is going to help us do. Okay, pretty close to the end here. I'd like to return to the future of engineering. In this room, I'm preaching to the converted, right? When I showed those slides at the beginning that talked about the shortage of engineers, where the US ranks, talking about here at the University of Michigan, a center of excellence for engineering, within the state of Michigan, a center of excellence for engineering with a rich history in manufacturing and innovation. It seems that data seems a little far away and remote, but believe me, we cannot hire the engineers that we need to solve some of these challenges because there aren't enough of them. And it's because these people are coming, right? There's not enough of them, but all these industries around the edge of this circle, they're all competing. So what I hope that I've done, and I'm talking to the younger generation here rather than the seasoned people that are here, I hope that I've given you some insight into what we're doing in automotive, and I hope that I've given you some excitement of perhaps a future career for you, and you could be some of the people who are solving these problems. And we don't know when we're going to see an autonomous car, a really autonomous car on the road. It might not be me that's putting it on the road. It might be one of you. So think about that. Could you be the person that's putting an autonomous vehicle on the road? Thank you very much for the time today. It's been my pleasure.